All right, so I know we've already talked about some of the convergence tests, but first let's talk about what you should look at first. In order for any series to converge, it must be true that a sub n goes to 0. Therefore, if a sub n does not go to 0, you know that that series diverges. Now, just because it does go to 0, like if a sub n goes to 0, that does not imply that the series converges. Okay? If the series converges, this must be true. The converse is not true. Okay? But you do know, because of this piece, that if that series does not, or the sequence, excuse me, does not go to 0, then I must diverge. And that's known as the divergence test because it's a quick way to be like, oh, well, I'm not going to be able to add all of those things up. Okay? So for example, if I look at A and I'm looking at the limit as n goes to infinity of my sequence, this goes to 1/3. That's not 0, so this whole thing must diverge. If I have 1 over n cubed, it equals 0. Okay? Therefore, there's another test that I would then need to do. So like keep going with this. Okay? All right, let's look at the limit as n goes to infinity of e to the 1 over n squared. Now using limit properties, I can take this to be e to the limit as n goes to 0 of 1 over n squared. The limit as n goes to infinity of 1 over n squared is 0, and e to the 0 is 1, which is not 0, so this diverges. Okay, so all that it does is it just lets you know, like, oh, it diverges. It might be like, oh, I need to do something further to see if it is convergent. But if the sequence does not go to 0, the series must diverge. So let's talk about the integral test. So if you end up having a function that looks like you could take the integral of it, or a series that if you map it to a function, looks like you could take the integral of it. So if you look at some function representation, and it is positive, continuous, and decreasing, and we can make that function happen, okay, for some positive integer n, then it must be true that both of these series converge or they both diverge. So as long as f is continuous, decreasing, okay, and then you're going to end up having positive outputs here because it needs to be a decreasing function and it's going to start positive, so that's going to happen. Then if you can map it to a function and do the improper integral, then you can figure out if they both converge or diverge. Now that area is not the same as the sum, so don't get those confused. It doesn't give you the sum, it just helps you find the area or find out if it converges or diverges. So let's go back to that one we just said, like, oh, I need some more info here. So checked it, it definitely goes to 0 for the terms of the sequence. And so I'm going to take the integral from 1 to infinity of 1 over x cubed dx. I know that 1 over x cubed is continuous on 1 to infinity, and I know that it is decreasing as well. All right, that's x to the negative 3. So I end up getting x to the negative 2 divided by negative 2. Let's put the negative up here. 2 here. From 1 to infinity, when I plug infinity, I get 0 minus negative 1/2. So converges because the integral converges, so this series is going to converge. All right, let's look at the integral from 1 to infinity of 1 over the square root of 2x minus 1 dx. Now I could look at a graph of this to see continuous, decreasing, all that good stuff, and it is. You can check it, you can verify it. All right, the antiderivative is going to be 2 square root of 2x minus 1, but then I have a term on the inside that's linear, so over 2. So those really just go away from 1 to infinity. Oh no, when I plug infinity, this diverges, so this also diverges. All right, when you have a series that is just n to the p, so like we had that 1 over n cubed that we just looked at, right? We call that a p series. And that's a very specific form of series. And so notice just in summary here, and if you have taken those notes in class, you already kind of know this, but if p is greater than 1, then that series is going to converge. And if it's less than or equal to 1, then that series is going to diverge. This is going to be really helpful when we do some comparison tests later on. Note, you can't just use this on this one because it's not n to the 1/2. Like there's more stuff in there, but we could use it as a comparison test, which we'll talk about that later, that you know this one diverges, and so therefore this one has to diverge if you didn't like the integral test. All right, let's look at some more examples using that. So because it's 1 over n to the p equals 4, and that's bigger than 1, so this one is a convergent series. In this one, p equals 2/3, that's less than 1, so this is going to be a divergent series. That's it.